All right, welcome back to part two. Today I'm going to debunk everything I just told you in part one. Well, not really. We're going to actually deal into the nitty-gritty. But before we start that, I wanted to go back and talk about this measuring reaction rates, which I kind of flew through last time. And this is important because in the lab, you're actually going to be doing this kind of stuff. If you were actually going into the lab, you would be doing it hands-on. But one of the ways that we determine the concentration, so we can measure the change in concentration of a substance, and it doesn't matter if it's the reactant or the product, because I can relate them back to the rate by that rate expression, as a function of time, is absorbance using a spectrometer. And there's a particular relationship that allows us to do this. This is called Beer's Law, named after a guy named Beer, not because he really liked beer a lot. Okay, so Beer's Law. And Beer's Law looks like this. It's your ABCs. Big A is absorbance. C is your concentration. A and B are going to be dependent upon the system that you have. So B is the path link of the cell that's going to go into, so the cuvette you have that you're putting your solution in. This is usually 1 centimeter, so it usually just falls out of the equation. And A is a constant. And A is going to depend on whatever your substance is. And so this allows you to directly relate. If I set this up so that I measure absorbance versus concentration, what I should see if I'm looking at a reactant, if I have absorbance versus concentration of a reactant, that concentration is going to go down over time. I should have a linear relationship. So as I reduce the amount of reactant in that solution, my absorbance is going to go down. A and B are going to be the same because A is my constant that's unique to whatever my reactant is. Let's say this is reactant A2, then A is going to be constant throughout this reaction. B is going to be constant because I'm going to be using the same path length, the same cell, so I can relate absorbance directly to my concentration. And in this way, we can look at the change of concentration over a period of time by measuring its absorbance. So I could look at my absorbance over time, and I'm going to see where that's going to go down. As the time of that reaction goes, my absorbance of my reactant is going to go down. If I look at the absorbance of a product, so let's say I have AB as my product, then I should see something like this over time. So I would start with 0 amount of product, and then as that reaction proceeds, the concentration of my product as I go up is going to increase. So I could do that as a concentration, but I could also look instead at the absorbance. So because I can relate absorbance directly to the concentration. If in your reaction you have, let's say, A2 plus B goes to AB, only one of these can absorb in the visible spectrum. So only one of these. So if A is my analyte that absorbs, then if B absorbs, then that's going to throw off my measurements here, or AB absorbs, and that's going to throw off my measurements. So I want to set this up so that I have a chemical reaction where only one of those things is going to absorb in that spectrum. And so that's what this slide is kind of showing, is whatever I have in my sample, that sample is going to be either a reactant or a product, and only one of the things in that reaction can absorb. I'll have a detector here that's going to detect how much of this is in solution based on how much of the light it's absorbing, and then I'm going to be able to graph that and experimentally determine. So that's often how we get these values that we have in kinetics, is we're looking at the change in concentration of something over a period of time by looking at spectrometry. That's going to be one of the easiest ways. Okay, so moving into what we're going to cover today. So today we're going to learn the difference between reaction rate expression, so that's what we talked about in part one, and reaction rate laws. And so rate laws are really experimental, determined, mathematical type of relationship, as opposed to our rate expression, which was very stoichiometrically driven. We're going to understand the difference between reaction orders and how a concentration affects the overall rate. And in our Zoom meeting, we're going to do a lot of calculations determining reaction order. So how do you determine it? And then we're also going to just note what those units of rate constant are. So that's what we're going to do today. So let's just go back and remember what our rate expression was. So if I have A plus B goes to AB. And let's say this is a 2 and a 2 and a 2. My rate expression is going to take into account my stoichiometry. So I could say that my rate equals the change in concentration of my reactant over some period of time, either reactant, or I could look at the increase in concentration of my product over a period of time. And my stoichiometry here is going to be 1/2 since this is a 2. So this is my rate expression. This implies that as one of these goes, and 2 of these is formed. That is unmessy life. So this is not really, this may be the case, and as this decreases, this is formed, but this could also not be the case. And so what if I looked at this reaction, I looked at A2, for instance, versus time. And what I saw with A2 is A2 goes like this, but my concentration of my product goes like this. What that's going to tell me is that this is having very little effect on the production of AB, because this is going down significantly. This is almost gone before I see any appreciable product. And so this might tell me that A2 is not really affecting the rate of that reaction. Maybe I look at B, so let's look at B2, and B2 looks something like this. And so now what this means to me is that B2, this reactant here, is really controlling the rate of that chemical reaction, because as this goes down, it looks like this is going to go up at the same rate, whereas A2 is being depleted very fast, but that's not really affecting the overall rate of that reaction. This means that my rate expression is not going to really give me an idea, because if I wanted to know the rate of this reaction and I looked only at A2, that's not going to give me a very realistic idea of what's going on. I could look at B2, and B2 may give me a realistic view of what's going on, but I don't really know. And so in chemistry, rate expressions, we'll come back to rate expressions, but these aren't very helpful unless the reaction happens in one step, meaning there's only one event that's happening. A2 is reacting with B2 to forming AB. But what if you need multiple steps? What if in this scenario, for this reaction to happen, A2 has to go to 2A first, and then A can react with B2 to form AB. Now I have a 2-step reaction. This may happen really fast, so I would see A2 going away really quickly, and then this would be my slower step. This is going to be what determines the product, the rate of that product being produced. And so this would be step 1 would have to happen, and then step 2 would have to happen, and then these two together would be the overall reaction. So now if I look at A2, A2 is not going to give me a realistic idea of what's happening in that chemical reaction. And so rate expression is not going to help me here. So I'm going to look at a mathematical relationship. So that is what we call the rate law. And rate law rules. So rate law is over rate expression anytime. And this is a mathematical relationship. This is going to give me an overall look at the reaction, but I'm going to take each reactant and evaluate it independently. So I can no longer do this blanket rate expression where I treat A2 and B2 the same, and I say that as this concentration decreases, that equals the same amount of this concentration decreasing, which equals 1/2 of this concentration increasing. Now I can't do that. My rate law is going to look at them all independently. So I'm going to look at A2, then I'm going to look at B2, then I'm going to combine those together and come up with an overall rate law that treats each of those independently and then expresses what that overall reaction rate is. Rate laws look like this. And rate laws, I only have reactants in. So I'm not going to put a product in my rate law. My rate expression, I looked at it as a function of product production. Now I'm only going to look at my reactants. My rate equals K, this is little k, times A to the N. This would be my overall, my rate of the reaction. This is called the rate constant, and that's going to be unique to that chemical reaction that's happening. This is my reactant A, and this N here is called the reaction order. So N is experimentally determined, and it weights the effect of a reactant on the rate. So if this is 0, then that means this has no effect. If this is 1, then this is directly proportional. If this is 2, then this is exponential. So it's going to weight the effect that that particular reactant is going to have on the reaction order. If I have a chemical reaction where I have more than one reactant, so let's say I have A plus B goes to AB, now my rate law would look like this. I would still have a rate constant. Then I would have concentration of A to some power times the concentration of B to some other power. And N and M could be the same or they could be different, because remember, we're going to treat each reactant independently. Meaning I'm going to find the effect that A has on that chemical reaction, then I'm going to find the effect that B has on the chemical reaction, and they may or may not have the same reaction order. So N and M are my reaction orders. So I'm going to have a unique one to each. So they could both be a 1, or this could be a 0 and this could be a 2, or this could be a 1 and this could be a 2. So these are going to depend upon the chemical reaction itself. So this would be my overall rate law for a reaction where I have 2 reactants. Let's say I have A plus B plus C goes to ABC. Now my overall rate law would look like this. K A to the N, B to the M, and C maybe to the X. So now I'm going to have 3 different reaction orders. Or they could be the same, but they're going to be independent to the reactant itself. And so I'm not going to put the products in these rate laws, only the reactants. So if I have a very simple reaction where I only have 1 reactant, then I am only going to have 1 reactant in my rate law. If I have 2 reactants, then I'm going to have 2 reactants in my rate law. So reaction order is going to tell you the effect that that reactant has on the chemical reaction. So reaction order is really important. In this chapter, we're only going to look at 3 scenarios, 3 different types of reaction orders: 0, 1, and 2. You can have any number of reaction orders. You can have a reaction order of 0.5 or 1.4. Then it starts to get really complicated. So we're just going to look at 0, 1, and 2. And that already gets us very complicated. So let's just say I have a very simple reaction where I have A going to B. So I just have 1 reactant going to a product. My rate here would be equal to K A to some reaction order. And B I'm going to leave out of my rate law. So very simple reaction, only 1 reactant. So if N equals 0, what that tells me that is my reactant is 0 order. And my rate is independent of reactant A. So that means my rate then would be equal to K times A to the 0. This is going to fall out. My rate would just be equal to my rate constant. I'm independent of my reactant concentration. So I could start with 2 molar A, I could start with 1 molar A. I'm not going to see a change in the rate of that reaction. It doesn't matter how much concentration of A that I start with if I have a 0 order. So A just basically falls out of the rate law. When N equals 1, this is my reactant is first order. And then my rate is directly proportional to my concentration of reactant A. So then my rate law would look like this, K A to the first power. So if I start with 1 molar concentration, I'm going to have a particular rate. If I start with 2 molar concentration, then my rate's going to be double. So these are going to be directly related if this is first order. If N equals 2, now my reactant is second order, and my rate is proportional to the square of concentration of reactant A. So now I have an exponential scenario. So if I have my rate law is going to look like this, if I double my concentration of A, that's going to quadruple my rate. So if I start with 1 molar, then I'm going to have a certain rate. If I start with 2 molar, now my rate is going to be 4 times that amount. So that means that the concentration of A has a very significant effect on the overall rate of that reaction. If I were to just kind of draw out what these would look like as opposed to the function of rate versus the concentration of A. So if I have 0 order, as my concentration of A goes down, right, then this is going to be essentially flat if I'm zero order. So it doesn't matter what's happening with this x-axis, my rate is going to stay the same. If I have n equal 1, now it's going to be directly proportional. So as my concentration of A increases, we're going up here, increases from 0 to 1, then my rate is going to go up, right? So if I have a reaction and I run it at 1 molar starting concentration of A, I would have this rate. If I started with 2 molar, so let's say this is, maybe we'll go from 0 to 10 here. If I go to 2 molar, now my rate's going to double. So this would be an n equal 1. If I have n equal 2, I'm going to see this exponential increase here. So reaction orders. Reaction orders are hard because you don't get these from stoichiometry. So you can't look at this. I can't look at this reaction and say, well, this is a 1-to-1, so it must be first order. The stoichiometry of this reaction gives me no idea about this. So I can't use stoichiometry here. This is all experimental. You have to have data, then you can determine what's happening. How do we determine reaction orders? You can only do it experimentally, and they're not related to stoichiometry. So a common way to determine is you have the initial rates method. So if I'm going to determine reaction orders, and there's many ways to do this. One method is the initial rate method. And in this, I'm going to have the rate is going to be measured for the reaction over a short period of time. So this is going to be your average rate. The shorter the time span, the better your average is going to be about what's happening at the beginning of the reaction is measured. And so the amount of time that you use is going to depend on whether you have a really slow or really fast reaction. So if you have a really fast reaction, then your short period of time is going to be much smaller. If you have a slower reaction, then you have a little bit more time to play with that. Then I'm going to run the reaction several times using different starting concentrations of my reactants. So I'm going to run this reaction many times. I'm not just going to run it once. I'm going to run it maybe 3 or 4 times. And each time I'm going to vary the concentration of one of my reactants, and I'm going to measure that rate. I'm going to measure the rate for a given period of time for each of these reactions where I'm varying the concentration. And then I'm going to look at the effect varying the concentration on a reactant has on the rate. Then that's going to allow me to determine reaction order for each reactant. So it sounds really complicated. This initial rate method is really very simple when you start to look at it. One of the things that you're going to see here is you're going to see a graph or a table that looks like this for this initial rate method. So I think the problem with this chapter is figuring out how do you use which equation to look at which. And so an initial rate method, because you have different amounts of rates, you're going to have some period of time, and you're going to start at time 0, and then you're going to go to maybe 10 seconds, 20 seconds, so forth. You're going to have a certain amount of time, and you're going to measure that same time for each. So you may not see time in your table, but what you'll see is your initial rate and your concentration of your reactants. So let's say I have 2 reactants, and I would have my initial concentrations of that, and I would have my experiment number. So maybe I'd run this 1, 2, 3 times. I'm going to vary my concentrations here, and I'm going to have some initial amount of rate that I've measured over the same period of time for each experiment. So that's what it's going to look like. You may not see a time column here because the understanding is that each of these experiments, this rate was measured over that same amount of time. So what you're going to look for is the effect that the concentrations of these would have on the initial rate. So let's say I have 1 molar here, 1 molar of each. So my first experiment I run, and I'm going to use 1 molar of each of these. And my initial rate of that is 0.083 molarity per second. Right, so I'm going to have units of molarity per second because that's my rate. And let's say I run it and I double B, but I keep A the same, and then my reaction rate is still. So now I started with this reaction, I have double the amount of B than I did up here, and the rate did not change. So this tells me that B is not really affecting the overall rate of that reaction. If I run it again, I'm probably going to drop B down back to 1 molar, and maybe I'll double A and see what that does. And let's say I double A, and then I get 164 millarities per second, then this means that if I'm going to compare here to here, I actually doubled the rate by doubling A. So that tells me that A is going to be first order and B would be zero order. So I'm going to compare these rates of these reactions, varying concentrations of my starting reactants. And so these are three separate chemical reactions. What I've done is I've varied the concentration of my starting reactants and then measured and then compared the rates of those. All right, so I'm going to do a problem with you. So let's look at these experimental results here. Let's say I have a simple reaction where I have A going to products. So I only have one reactant to worry about. And I want to determine the reaction order. And let's say I set this up and I'm going to use my method of initial rates to determine reaction order for reactant A. And then I'm going to plug that into this equation here. I want to find N here. That's my reaction order. And let's say this is a scenario that I have A, and this is in units of molarity, and then I have my initial rate. So that might be the first 10 seconds of that reaction. I was able to measure the rate of that. Let's say I ran 3 different experiments. So I have experiment number 1, number 2, number 3. And my first one, I start with 0.1 molar of A, and I have a rate of 0.15. And this is in units of molarity per second. And then let's say my second reaction, I double the amount of A, and my rate here goes up to this. And then let's say here, now I triple the amount of rate. Well, actually, let's do this. Let's double from where we went to here, and let's say now my rate here is this. I might be able to eyeball this and figure out N. So the way that I'm going to use this data is I'm going to pick 2 experiments where my concentration of my reactant changes, and I'm going to compare the rate and see how did the rate change. And that's going to tell me the effect. So here I might pick 10.1 to 0.2, that's a factor of 2. So I doubled. I might look at my rate here and say, did the rate double? The rate also doubled. So that means that this is going to have a direct effect. So as I double this, I'm going to double the rate of this reaction. If I look at this, I double this, I double this. So this is 2 points that tell me the same thing, that N is 1. As I double the amount of A that I'm starting with of that reaction, my initial rate also doubles. So my rate law for this would be K A to the first power. This would be a first order, because as I doubled the concentration of my reactant, my rate doubled. Let's say I have the same scenario, but now let's say I have experiment. I ran this 3 different ways. 1, 2, 3, and let's say these are my data. My molarity of A and my initial rate. It's a molarity per second. Let's say I do 0.10, 0.20, 0.40. But now my initial rates here are 0.015, 0.060, and 0.240. So I'm going to compare. Here, I double my concentration, but here, I'm quadrupling. So I'm going from, so this is a 4 times. So this is going to tell me that I'm second order. N equals 2, and my rate law for this is going to be A squared. If it's not easy to just look at this and find, there's a way that you can also do this mathematically, taking your rates. So it's not always easy to see what's happening here. So you can eyeball it, or you can use this equation to find N. So I have rate of 2 over rate of 1. So I'm just going to compare. It doesn't have to be 2 and 1, but I'm just going to pick 2 of these where I want to look at the concentration of A and how that's affecting. So I just picked 2 of these. Maybe I picked 1 and 2, maybe I picked 2 and 3. And I'm just going to write rate laws for both of them and then put them over each other. So I usually do this so that the larger rate is on the top. So rate 2 then is 0.240 over rate 1. So I'm going to use 2 and 3 here. I'm going to use these 2 here. So this is going to be rate 2 rate 1. So I'm going to use these two here. So rate 2 is this, is my rate. Rate 1 is going to be this. I'm going to put the lower one on the bottom. And then I'm going to plug in my concentrations. So in this case, I have 0.4 molar, and here I have 0.2 molar. And I'm going to solve for N. So K is going to be the same, so K is going to fall out of that equation. So what that looks like is I'm going to have 0.240 divided by 0.060 is 0.40, 0.20, and I'm going to solve for N. Now I'm going to work out this with you because this is probably a mathematical operation that you haven't done a lot. I'm just going to work through this really quickly. 0.240 divided by 0.060, 0.4, 0.2. So I'm just going to pull those together, put that whole thing to N. This gives me 4 here, equals 2 to the N. This is going to divide and give me 2. So if I want to get N by itself, I'm going to take a log of both sides. So that's going to be log of 4.0 equals log of 2. And by doing that, it allows me to pull N out there. So that gets N by itself. So if I take the log of both sides, I can pull N out and N's there, and then I just do the log of 4 divided by the log of 2 equals N, and N is going to be 2. So I could find my reaction order that way. I could work it out. You can always fall back to this where you pick two of those experimental runs and just plug them into here. I do it easier to put your higher rate on the top and your smaller rate on the bottom, but you could do it either way. So this is an important sort of one of those mathematical operations from that mathematical operation sheet that you guys did to kind of reorient you if you've forgotten how to do that. Okay, I can also have a scenario where I have more than one reactant. So this is looking at a very simplistic way. So let's say I have H2 gas reacting with NO gas, going to N2 gas plus water. Now my rate law for this, I have to treat each of these reactants individually. So my rate law would be my rate constant times H2 to some reaction order, whether it's 0 first or second, and NO to some other reaction order, 0 first or second. So it could be any of those. So let's say that I calculate this out and it's first order for H2 and second order for NO. Then my overall rate law would look like this: H2 to the 1, NO squared. And this tells me that NO is going to have a larger effect on the rate of that reaction than hydrogen gas. It also tells me that there's probably multiple steps that are happening here. So hydrogen, there's intermediate steps that we're not seeing because we're just looking at the overall reaction, because this has an exponential effect on the rate, whereas this doesn't. So this is going to get hung up in that slow step, whatever is driving that reaction. All right, so I think this is where we'll stop here for today, and then we'll pick up in part 3 and expand on this. Okay, so I hope to see you guys there.